This app helps to understand how cross-validation works. And cross-validation, it's the way to detect possible overfitting in your model and actually find the optimal complexity of your model, so it's not overfitted. So let me start with explanation what you see here. So this is the plot. You have only sample in this case. And then you can see that this is X, this is Y. This is what is called a global model. It means this is the model made for all observations in your sample, right? So this is a standard error and this is the R squared. Now, what is the cross-validation? Cross-validation, it's the way to validate your model. When you take a part of your sample out, keep it out, make a new model, and then make predictions for this sample that you kept out. So this is what is called cross-validation. The simplest cross-validation is when you use one sample out. So you take the first point out, or the second point out, or the third point out, and that's what we have full cross-validation here. So let me show you how full cross-validation works. Now you can see all samples are ordered well. So this is X, this is Y, this is predicted value, and this is errors which we get in the future. So let's click run and wait. So first of all, you can see that every time we run it, you can see one point is shown as like a thick circle, right? Like this one, and so on. This is exactly the point that is out. So let me run it again. Yeah? Just follow this point here first. And then you can see every time you take it out, the slope of this line is a little bit different. So we kind of introduce this sampling uncertainty like we have seen in the previous app. We kind of emulate this sampling uncertainty and introduce it to the error. Okay. Now let me run it again, but now look at the table, right? So you can see that, so this is out, make predictions, out, predict, out, predict, out, predict. So when we predict the Y value for this particular point or for this point was not a member of the training set. So this point was kept out, so it was unknown for the model. And then we can compute the errors. We compute the R squared, the sum of squared errors, and then the R squared. And then you can see, for example, this is the R squared for the cross-validation, and this is the R squared for the global model. Then you can see that this is actually smaller because now it's not only fitting error, it's also a sampling error. Also, it's not a true sampling error, it's like an emulated sampling error or estimated sampling error, but this is smaller, right? Now let me show you how it helps if you use, if you have overfitting. Let's make a cubic model, right? So you can see the cubic model for this is the global cubic model. And you can see that the R squared is actually quite good, 0.976. This is the standard error, 0.52. Now let me run it and then look how different this model is now. We don't follow the regression coefficients in this case, but let's see how big the error will be. So although we use more complicated model, the R squared is worse and the standard error is also much worse, right? So comparing to the linear model, right? So let me show you the linear model again. So let's keep this one, 0.939 and 0.8. And then let's see what we get as a linear model if we use full cross-validation. So you can see that linear model actually performs better. So this one is, it was 0.8 before for the cubic model, and now we got 0.6, right? So the cross-validation tells you need to use linear model, not the cubic, because it gives you a better cross-validated performance, right? Although the standard error, you can see that the standard error for the global model is better if you use a cubic model, right? So if you look at these predictions, they are better if you change the complexity of your model to more complex one, to higher one. But if you use cross-validation, then it tells you that this model is actually better. So this is the way to tackle the overfitting and also to find the optimal complexity of the model. However, the full cross-validation is good if you have a small sample size. If your sample size is larger, like 30 or 50 observations, then it's better to use another cross-validation strategy, which I will show you too. It's random and Venetian. Let me start with Venetian blinds. It's called Venetian blinds. Look at this. These are the segments. So you can see we have 4 segments in this case. You can change number of segments in real software. In this app, I just fix it to 4. Okay. What it means? It means that the cross-validation will run 4 times. At the first time, all samples from segment 1 will be taken out. The rest will be used as a training set, make a local model, predict these 4 Y values, 3 Y values. In the next step, they get back, and then we take out the samples from segment 2, and then 3 and 4. Let's just look at this, right? So follow both. First of all, look at this one. You will see that you have 3 points. Every time we take a new run, we have 3 points. So actually we make 4 different models in this case. And then if you look at the table now, you can see which points are out, right? So the blue points are out on this stage. So we have 4 steps, so we have 4 different models, okay? So this is Venetian blinds. You can change actually the number of splits, number of segments, but it's very important that Y values order it in this case, right? So otherwise you will have some issues, unbalanced segments in this case. And then random, it looks more or less the same, but the segments are taken randomly, not systematically like every 4th or every 3rd, but randomly. So in my case, you can see that in this case, I got 1, 1, 1. So these 3 points will be out. Then these 3 points will be out. And then finally, you can see these 3 points and these 3 points, right? So if I run it now, you can see it. It's like more chaotic splits. Okay. So this is how cross-validation works. Play a little bit with different validation types, also with different models. And then you hopefully will understand this a little bit better.